start with that. So x equals 2 is a vertical asymptote. Then 0, 0 becomes the inflection point, IP. And then I have 3, 27. 3, I'm going to say 10, 20, 30, so 27 is here. Okay. The function opens up, decreasing from infinity to the inflection point. Okay. It changes concavity, decreases towards negative infinity on the left-hand side of the vertical asymptote. On the right-hand side, it's coming from positive infinity. It reaches a relative minimum, and then it goes to infinity. A lot of work. It was an interesting example. Y equals x cubed over x minus 2. Again, let's do this one more time together. Please, I'm hoping you're paying attention. So opening up, coming from infinity to the inflection point, where it changes concavity, opening down, approaching negative infinity on the left-hand side of the vertical asymptote. On the other side, it's coming from positive infinity, dropping to 27, opening up, relative minimum, and then increasing towards infinity. Be careful when you check how you put it in the graphing calculator. You have to put parentheses. Okay, so we have x cubed. Because it's one term, it's okay. And then we divide, but we need parentheses for x minus 2. I know the viewing window. It has to go further, higher, much higher than 27 for the y, right? So I can already adjust the viewing window. Negative 10 I don't need. Negative 4 is good enough. X maximum, okay, 10, that's fine. I think 8 will be enough. But y minimum, negative 4 is good enough, but 10 is not going to be good enough. I may want to go to maybe 30. I don't know. Oh, not 30. Oh, 27 is the minimum. At least 60 with a scale of 10. Now I click enter and I have to see what I have on paper. That's it. So as you see, it's coming from infinity. It changes concavity here. So I guess I should go to a little bit y minimum. I'm going to make it minus 10, let's say, so we can see a little bit more. So opening up, inflection point, down, the vertical asymptote is missing, but we know it's there. We have to graph it. And it's coming from positive infinity to this minimum point of 3, 27, and it goes up. We knew all this. We just wanted to check with the graphing calculator, which is fine. Any questions? Any questions? So section 4.5 basically puts everything together that we studied so far in this chapter. We've done this before, but now we're looking also at these limits when we studied, after we studied L'Hopital's rule. Okay, so allow me, so I think we have about 25 minutes or so. So we can look at that 4.2 that I skipped, and you will see why I skipped it. What was this? This was my page 12. 13. Okay. So 4.2 deals with two theorems. One is called Rolle's theorem. The other one is called MVT, or mean value theorem. Mean value theorem. So let's start with Rolle. They're related. That's why they're in the same section. So let's take a look at this scenario. I'm giving you the two examples. So let's look at this function. Starting at A, ending at B. And notice that f of A equals f of B. Here is a similar example. Still A, still B, still A equals B, f of A equals f of B, I meant to say. Okay, so don't look at the second scenario. Let's look at the simple one first. So here we have, so we're talking about Rolle's theorem first. Rolle's theorem. This mathematician said this. Hypothesis 1. F continuous on the closed interval a comma b. Is that true? So this is f of x. Is f continuous on the interval a comma b? Yes. Hypothesis 2. F differentiable on, not closed, at least the open interval a comma b. And of course the third one is that f of a equals f of b. And then he said this. If the function is continuous and differentiable, no cusp, no corner, and it's continuous. If it's continuous and it has no cusp or corner or vertical tangent, then it's differentiable. And f of a equals f of b, there must be a c in the open interval a comma b such that f prime of c is 0. In other words, there is a turn. In other words, there is a max-min. In other words, he said, if a function is continuous and differentiable and starts here, it has to have a turn, at least one, to come back down to the same y value. It can be this way, or it can be this way. But it has to have at least one turn. So this is an example in which it has more than one turn. So it starts here and ends here. It's continuous and differentiable everywhere. So it must have at least one turn. And I give you an example with 3 turns. But at these points, f prime is 0. We know that. Every time the function turns, it has to have f prime equals 0. So the same thing here, but this time I have a C1, I have a C2, and I also have a C3. And I can have as many as you want. But at least one is required for a function to start at this point and end at the same point. Being continuous and differentiable, it must have at least one turn. That's all he said. If these 3 hypotheses are fulfilled, there must be at least one value between a and b such that f prime of c is 0. In other words, there is a turn or a max or a min. They all mean the same thing. Of course, max or min, they're different, but a turn or max, or turn or min. So let's look at an example. So this theorem is in 4.2. Where's my book? Where's my 4.2? We're not going to do anything with this, just to verify that the function fulfills the conditions and draw the conclusion. That's all. There are other applications more sophisticated. That's all we need. The simple ones. So here it is. So let's choose 9, 10, 11, or 12. Verify that the function satisfies the three hypotheses of Rolle's theorem on the given interval. Then find all numbers C that satisfy the conclusions of Rolle's theorem. Anyone would like to pick a problem from these?
Number 9.
Okay, very good. So let's look at 9. For 9, we have f of x equals 2x squared minus 4x plus 5. The given interval is -1, 3. So first we have to verify 3 hypotheses. Number 1, do you think that f is continuous on the closed interval -1, 3? What do you think? Anyone?
Yes, because it's quadratic.
Because it's polynomial and quadratic, yes. Yes. As a polynomial. Awesome. Number 2, do you think that f is differentiable at least on the interval -1, 3? We don't care if it's differentiable at the endpoints. It may or may not be, we don't care. Do you think it's differentiable? For the same reason, polynomials are differentiable. Yes, because it's a polynomial. Number 3, f of -1 and f of 3. I don't know what that equals to, but very simple. I'll punch in the function in the graphing calculator. As you know, I like it. So I have 2x squared minus 4x plus 5. Why do I do this? Because it's so much easier to plug in 2 values and not have to do the same thing twice. Ah, okay, good. Are these 3 conditions fulfilled, or hypothesis of Rolle's theorem? Yes? Continuous on AB, differentiable on open, and f of A equals f of B. It starts and ends at the same point. Good. Then, by Rolle's theorem, there exists at least one number C in the open interval -1, 3, such that f prime of C is 0. There must be a max or a min there. So I have to find f prime. Can anyone give us f prime of x for this function? Anyone?
You said to differentiate
Yes.
the function. Sorry. For x.
Yep.
4x minus 4, sorry.
That's it. So I have to plug in C and then set equal to 0. So 4C minus 4 equals 0. Move 4 to the other side and get C equals 1. I have to show that c equals 1 is in the interval -1, 3. It's guaranteed by Rolle's theorem. Is 1 in the given interval? Is 1?
Yes.
Yes, that's it. Done. So Rolle's theorem says if these three conditions are fulfilled, you will find at least one value in this interval where the function has a turn. We don't care what it is, max, min, we don't care. We are just asked to show that the three hypotheses are fulfilled. And because they are fulfilled, Rolle's theorem guarantees at least one c in this interval, which we found, such that f prime of c is 0. We found f prime of x, we plugged in c, and we solved this equation with c in it. Move forward, divide by 4, we get 1. So 1 is in the given interval, and it's done. We don't have to write anything else. Any questions on this? Now the last theorem here, it's what it's called MVT. MVT, mean value theorem. It's based on Rolle's theorem. Slightly different scenario. So here's point A, here's point B. Of course, this is our function. So we have a function f of x, and it has 2 points on it. I connected them with the segment AB. And as you notice, this mean value theorem has only 2 hypotheses. It does not have the third one. And it's not possible. F of A does not equal f of B. So the first hypothesis, the first 2 are exactly the same. And there is no third one. That's a difference. So f continuous on A comma B. F differentiable on the open interval, and there is no third one. The same from Rolle's theorem. And here is what I would like to ask you before we continue. I know I only have, I have 10 minutes, I can finish, yes. So notice the following. I have the line segment AB, and I'm going to draw parallel lines to it. Parallel, 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 parallel lines, parallel lines, parallel lines, till the moment I can draw a tangent line. So I have this point, and I know that the tangent line at this point is parallel to the line passing through, or the secant line passing through the points AB. So I'm going to say tangent, secant line. So the tangent line and secant line are parallel. Tangent line to that point where x is c, and the secant line at that passing through AB, secant line AB, are parallel lines. Okay, so let's see what the conclusion is. Before that, actually. I would like us to determine the slope of this line, first of all. The slope of the secant line AB. I have this point, B comma f of B. I have this point, A comma f of A. So forget about the tangent line for a moment. What is the slope of the line AB?
F of B minus F of A over B minus A.
Excellent. F of B minus F of A over B minus A. That's done. Awesome. Now let's forget about the secant line for a moment. Can anyone give us the slope of the tangent line? So don't think in terms of AB. That's done. Now we want to determine the slope of the tangent line. They have to be equal. This and this will be equal. But before we set them equal to each other, we have to identify the slope of the tangent at that point.